Mechanics always starts with kinematics. So in this class, I like to give simple definitions of things. So I'll define kinematics as describing motion with equations and graphs. Describing motion with equations and graphs. In kinematics, you don't explain why something moves a certain way. You just describe how it moves mathematically. We'll explain why it moves a certain way later when we get to Newton's laws. So we're going to learn about kinematics through several examples. So let's look at example 1. And example 1 is a motionless body. This is the simplest example we can do. A motionless body, for example, would be me on a dance floor is a good example of a motionless body. However, in physics, when we say body, we don't usually mean, your body. We just usually mean any object that has mass, that we can think about its motion is usually what a body is. So in this case, our example is going to be this 1.8 kilogram stainless steel sphere that I call Hal. It's going to roll around on this one-dimensional track. Okay, so say hello, Hal. Hal is going to be motionless. It's going to sit right there. So let's draw our experiment here. So here's Hal. Here's sort of the solid track. And we want to describe this mathematically. We want to describe it with equations and graphs. So to describe the position of something mathematically, we have to draw an axis. Right? So we'll call this the x-axis. So this way is plus x, and we'll put the origin where x equals 0 right there. And we can think about where Hal is on the axis. That would be the equation part. And we can make a plot of where he is on the axis. That would be the graph part. Okay? So let's see. Where is Hal? Where are you, Hal? Oh, I have to look. I forgot. So I have my coordinate system over here. This is the origin. He's at about 40 centimeters. So if we wanted to mark it here, it would be at 40 centimeters on the x-axis. Let's look at the equation that would describe this very simple example of something sitting perfectly still. The equation would simply be x equals 40, and the unit is centimeters. So x we'll call the position, which equals where, I don't really want an equal sign, where something sits on an axis. Right? It's usually a function of time in kinematics. But in this case, it's a constant because Hal isn't moving. He's just sitting there. So that's the equation, x equals 40 centimeters. Let's look at the graph. Let's see, the graph is here. And in kinematics, when you make a graph, you always put time on the horizontal axis. You may be used to calling this the x-axis, the flat one, the x, the horizontal, the x. You got to get over that, because in physics, we put anything anywhere. So in this case, x is going to be on the vertical axis. You might occasionally hear a physics student say, I put x on the y-axis, because they meant they put x on the vertical. So you got to start calling them horizontal and vertical, or abscissa and ordinate if you want to go old-fashioned. So in kinematics, we always have our time on the horizontal axis. And basically, we are telling the story of the mass, or of the body. What happened to the body in time? Well, we'll put the origin here. At time equals 0, where was the body? It was at 40 centimeters. So we'll put a plot here. We'll realize that that is 40 and put a point there. And we'll wait a few seconds, right? Wait a few seconds and say, where is it? Still at 40. So we put another plot there. Then we wait a few more seconds, say this was 3 seconds, and we waited a few more seconds, and where is it? 40, right? So these kinematic plots are literally just a plot of what happened. In this case, the position versus time. So that's the simplest kinematics plot you can get, something that is just not moving, and it's just a flat line because the position didn't change versus time. It's as far down as we can go. They'll get more complicated than that as we go. But that's the beginning. That's how we get started in kinematics. All right, our next example, example 2 for kinematics, is a smoothly rolling body beginning at the position xi. So the subscript means the initial position, xi. And actually, we don't really want to do rolling. So we will eventually talk about rolling motion, very complicated. Right now, we just want to imagine the body just moving. So our demo is going to be Hal again. And the reason Hal is a nice shiny object is you can't tell that he's rolling. That's the idea. Now, Hal has been around a while and getting some rust spots there. So, you know, I know how you feel. Trust me, I get it. So you might be able to tell that it's rolling, but just pretend that you can't tell that it's rolling, because I can't afford another steel ball. They're kind of expensive. Okay, so we're going to move just like that. There's your demo. So let's think. Hal started here. We'll call this xi. We'll call this the origin. And there you go, uniform motion. And it's not rolling. It is, we'll just say moving. And we'll ignore the rolling. Okay? So we saw it. Now let's first graph it. We're going to describe the motion with equations and graphs. So for the graph, we're going to do the same thing. It's going to be time on the horizontal axis, the x position on the vertical axis. We know that at time 0, we always put the origin here, 0, 0. We know at time 0, it started at xi. So you would plot it like this. You'd say, you know you started here. So at time equals 0, it was there. And then you could think, we're telling the story of Hal's motion. So we had 1 second, 2 seconds, 3 seconds, 4 seconds. And if we were to plot where it went, we know that in time from 0 to 1, it got a little bit higher, right? So I could put a mark there, a little bit farther along the x-axis. And in another second, it got a little bit farther along the x-axis. And in a third second, it got a little bit farther. And after 4 seconds, it got a little bit farther. And when we say smoothly, we kind of mean, more accurate might be uniformly. Might be a more descriptive word. So if it's moving uniformly, that basically just means it's going about the same amount of distance x in the same amount of time. That's what we mean by that. So if you have something that is uniformly moving, these points together make a line, right? So I could draw a nice line through those points. That is the kinematics graph for something moving uniformly. So the property we're going to talk about is that the body has velocity. Velocity. So if we had to define velocity, it is the rate of change of position with time. We're going to talk about several kinds of velocities, but that is the basic idea. It's how fast is the position changing in time. The symbol for velocity looks like this. Now, I don't know if you're going to know what that is. That is a cursive V. I know they don't teach cursive anymore. They used to teach us how to write in cursive. So if you don't know what weird symbol that is, that's my cursive V. I always use the cursive symbol when I'm talking about velocity. I use the regular symbol when I write the word. Okay? Now, here's an example I can prove to you. This is my, one of my 4th grade cursive assignments. Look at that. It's beautiful. Look at that. Look at how good look how good I cursive in the 4th grade. Now here's the grade. What? Give me a break. Oh, I was so mad about that. It's destroyed my 4th grade GPA. But I don't hold grudges, so I'm completely over it. So this is the symbol, cursive V. The unit, it's in meters per second. And we'll get more into the math of it in a minute. I just want to point out another thing. It is the slope. If you've taken some algebra and done some plots and you know what slope is, it is the slope of the xt graph. And by that I mean the kinematics plot that you make, or the graph you make when you put t on the horizontal axis like you always do, and you plot position on the vertical axis. Right? So if we were to take this line and find its slope, that would be equal to v. Okay? So now next we'll move on and do this a little bit more mathematically. Example 2 was interesting. Why was it interesting? Because something changed. All right, in example 1, pretty boring. Hal just sat still. But example 2, Hal moved. And that's what made it interesting. Actually, I'd go further. I would say it was fascinating. So since something changed, we need more variables. If we're going to get to the equation part of that example, we need a little bit more. So first, let's recall we know what x is. That's position. But for example 2, it changed with time. So we'll say AFO time. So you got to get used to some of my abbreviations. AFO means as a function of. Okay? I'll introduce you to T2 later, 2 equations, 2 unknowns. But for now, we're just doing AFO. Right? So we knew that there was some x. We know it can change in time. We call it position. But now we need a new one. Okay? So the new one, we write delta x. We call this the displacement. The displacement, it equals the change in position, and here's the key difference, between 2 times. So a little bit of a difference. This one continuously changes in time. This is really 2 different times. So let's look at our equations. We're not going to quite get to the equation that describes the motion yet, because we need to really obsess with displacement for a minute. Let me give you an equation for displacement. It's equal to a final position minus an initial position. Like I just said, it's the change in 2 positions. Now in physics, you got to make sure you always get this right. It's always final minus initial. So I can give you an example. Say you go to Starbucks with $10 and you get a cup of coffee and you come out with $8. Right? What's the difference in your money? Just say it out loud. What's the difference in your money? Wrong. The difference in your money is negative $2. So I'm sure you said $2. Everybody says $2, but it's negative 2. It's final minus initial. It's $8 minus $10. So in physics, we got to keep up with these negative signs, and changes are always final minus initial. In language, we have words that mean the negative sign. I just blew $2, or I just lost $2. Or I just dropped 2 G's on some dubs for my Civic or something like that. So in that case, dropped means it's negative. But in physics, we have to get everything formally correct. Final minus initial, the numbers can be negative. Okay? Let's see. So we want to be sure we understand this. What do these mean? The position xf occurs at time t final. So if we were tracking the motion, we might have an initial time, and it's at one place at the initial time. We might have a final time, it's at one place at the final time. And you can imagine that the position x initial occurs at t initial. 2 different times. These are positions, and that's displacement. Okay? Now, here's the tricky part. Here's where I'm going to deviate from most physics books. Most physics books start out with 1D kinematics, and that's all we're doing, one-dimensional kinematics. Only one way to go on the track. And therefore, they ignore vectors until they get to 2D kinematics. But I like to just bring in vectors right at the beginning. Let's just get it over with and talk about vectors. This is just life, right? Delta x is a vector. And that's why I put a vector symbol on top of it. Delta x is a vector. We have to deal with it, even in 1 dimension. So let's think, what does that really mean, that it's a vector in 1 dimension? What are we talking about here? And the way to think of it is we could imagine, let's go back to our x-axis, right? Here's the origin. And if I give you a delta x vector, a displacement vector, say equal to 3, what does that mean? That means I was at some position x initial, and I had some position x final, and the distance between them is 3. And the fact that it's positive means it's to the right. So that would be plus 3. If you get a negative value, then it would be the other way, right? We could also have plus x, there's the origin. Doesn't actually matter where the origin is when you're talking about displacements because they're just a change. But let's say delta x equals minus 2. That would be a case where you have an initial here and a final here, and the vector from initial to final points that way, minus 2. Okay? Now, one thing about vectors is you always have to have both sides be a vector, right? So you know a vector is a number with a direction, a scalar is just a number. So I said delta x is a vector. Clearly there has to be something to make 3 a vector, and it's called the unit vector, I hat. You put a little hat on it. And here, minus 2 I hat. I corresponds to the x-axis. Hat means it's a unit vector. It's just a little thing you put on there to say x-axis direction. And unit means its magnitude is 1. So you're multiplying these two things, but you're multiplying 1 times 3 is just 3. 1 times negative 2 is just negative 2. All it's really doing is identifying the direction. Okay? So right now, if you've never heard of that, that's freaking you out. You're panicking, screaming, turning off the computer. So don't worry about it. We'll do a lot more unit vectors. You'll get comfortable with it in time. But for now, to be formally correct, if I'm calling this a unit vector, I should probably say, okay, it's this difference, and put an I hat. I'll show you other ways to do the vector notation later, but for now, I want to put that on there. And we're going to think of these things as vectors.